Hey guys, in this video we're going to show that anti-differentiation is linear. Now what that means is that if f of x and g of x are functions, what that means is that the antiderivative of k1 times little f of x plus k2 times little g of x, the antiderivative of that with respect to x is actually equal to k1 times the antiderivative of little f of x with respect to x plus k2 times the antiderivative of little g of x with respect to x. In other words, we can actually split up the integral over the addition sign. We can split up the integral over the addition sign, and also we can just let the constants hang out at the front there. We can pull them out of the anti-differentiation sign. By the way, the anti-differentiation is also called integration and integral. So call it whatever you like. I'm going to stick with anti-differentiation because that's what I introduced it as. So the antiderivative of k1 times little f of x plus k2 times little g of x with respect to x is equal to k1 times the antiderivative of little f of x with respect to x plus k2 times the antiderivative of little g of x with respect to x. We're going to show that that's true, and that's called linearity. All right, so to show that that's true, suppose also that big F of x and big G of x, big G of x are functions such that f prime of x equals little f of x and g prime of x, so big G prime of x, equals little g of x. Then let y of x equal k1 times big F of x plus k2 times big G of x. Now we know from differentiation that when you differentiate a function, you can also split it up across the addition sign, and you can also let the constants just hang out the front. And so that tells us that if we're going to differentiate y, big Y, with respect to x, it's actually going to be equal to k1 times big F prime of x plus k2 times big G prime of x. And that's fantastic because we know that big F prime of x is actually equal to little f of x, and also big G prime of x is equal to little g of x. Therefore, y prime of x is actually equal to k1 times little f of x plus k2 times little g of x. And now, from our theory on anti-differentiation that we did in the last video, we know that the antiderivative of this thing, the antiderivative of big Y prime of x, must actually be equal to big Y of x plus some constant. Therefore, the antiderivative of k1 times little f of x plus k2 times little g of x with respect to x must be equal to big Y of x plus a constant, which is equal to k1 times big F of x plus k2 times big G of x plus a constant, because big Y of x was equal to k1 times big F of x plus k2 times big G of x. All right, we're nearly done. What we need to observe is the following, that this one here, this c, is actually just some arbitrary random constant. It's just some random number. And therefore, I can kind of split it up. We can actually split this thing up as k1 times big F of x plus, and I'm going to write k1 times c1. So it's just some random number c1 times k1. So plus k1 times c1 plus k2 times big G of x plus, again, some random number c2 times k2. And now, since c1 and c2 can be any random numbers we like, then when put together, k1 c1 plus k2 c2, where this k1 really is this k1 here, but the fact that we're multiplying it by a random c1 just changes it into a random number altogether. Similarly, this k2 is the same as this k2 here, but the fact that we're multiplying it by a random c2 just makes it a completely random number again. When we add these two terms together, because we have two random numbers, we just get another random number c. So yeah, k1 c1 plus k2 c2 equals little c, because they're all random numbers, and so when put together they represent one random number. Okay, so nothing against the rules there, it all works out to be correct. And now what we're going to do, the reason why I multiplied by k1 and k2, we're going to factorize those out. So this is equal to k1 times big F of x plus c1, where c1 is just some arbitrary constant, plus k2 times big G of x plus c2, where we factorized out the k2, and of course c2 is just some arbitrary constant. And then we're nearly done, because big F prime of x equals little f of x. That tells us that the antiderivative of little f of x dx is equal to big F of x plus some arbitrary constant c1. So what we actually have here is k1 times the antiderivative of little f of x dx plus, and for exactly the same reason, since big G prime of x is equal to little g of x, then it turns out that the antiderivative of little g of x must be big G of x plus some arbitrary constant c2. So plus k2 times the antiderivative of little g of x dx. And then we're done, because this is exactly what we set out to prove. We showed that the antiderivative of k1 times little f of x plus k2 times little g of x is equal to k1 times the antiderivative of little f of x dx plus k2 times the antiderivative of little g of x dx. So we can just drag the constants out the front of the integral sign and also split the antiderivative up across the addition sign. All right, thanks very much for watching. See you guys later. Bye.